Yeah, see, this last week two port related problem in graded assignment.
Okay.
This gate parameter. I think there is some error in answer, or
Question 5 you are talking about?
yeah, from question 5 onwards till
Question
10.
5 to 8, that common data question on set parameters 5 to 8, right?
Yeah, yeah.
Yeah, the answer key was wrong. That was taken care today while evaluating. You can see the scores once it is pushed to the dashboard.
Okay, okay. Thank you. Just wanted to tell that.
Actually, somehow the answer key given for that 5 to 8 was by mistake. It was the same answer key as the 1 to 4. Point
Correct,
5
correct.
minus
Yeah,
0.25.
yeah.
Why
Yes.
somehow it happened so, and that was rectified right now for evaluation.
Okay, okay. Understand. Thank you.
Yeah. So we were just discussing in the last class till that impulse response, right? So we are just into looking into this introduction to body plot. So I think
Yeah.
till that it's fine for you. What has been?
I think the Bode plot you're going to explain today.
Yeah.
Yeah, better because a lot of doubts in that. So yeah.
Yeah, we will just start looking into the body plot and maybe detail more solving on body plots. We will continue on Thursday also. I think Friday 19 is your deadline, so we can take time for understanding.
Hmm.
Right now we have come till the impulse response, talking about the impulse response of the system,
Okay.
and just we had done plotting, given the transfer function, finding the poles and zeros of the transfer function, and then mapping it onto the S plane. And we
Okay,
had seen
understand.
one typical example in the last class for that complex conjugate pairs also. So today we will be just starting with the this frequency response plot, which is the body plot, and then finding how to find the corner frequency, all those things. And
Yeah.
slowly we can maybe take some time of Thursday also to understand. After which we can devote for the revision sessions.
Yeah, that will get. Can you take some example and do border plot?
Yeah, we will do. Better
Yes.
first we will discuss the same example as in the lectures, then those in the practice assignment as well. So
Yeah.
that later you can try with the ones in the graded.
No. Yes. Yes.
And regarding that week 11 graded, in addition to the question that you have pointed out, that is the common data question, question number 5 to 8 in the portal, and as well as question 10. Question 10 also had a mistake in the answer. I mean, the question 10 was MCQ. You had one dependent voltage source, if I remember correct, that alpha V1.
Yes. Yes.
So which was some MCQ. So with that R1 and R2, it was swapped actually in the figure and the in the multiple choices given.
Yeah. So in
So
one I was getting R1 actually, but there was no
yeah,
R1 option.
correct. That's because the reference was wrong. I mean, the R1 R2 in the circuit and in the choices, it was swapped between R1 and R2.
Okay, and then I think minus will not come. One minus alpha we are getting, and
So
yeah.
with that, you had no right answer in the choices given. So for that, it was removed out of valuation. Okay.
Okay. Okay. Yeah.
For 5 to 8, it will be reevaluated with the right answer for that those set parameters we were talking about. And for this question 10, since it was an MCQ, no other go other than removing it from the valuation. So that 2 mark question will not be evaluated.
Okay. Okay.
Question 10.
Ma'am, can I have your comments on question 15 as well?
Question 15 on the transformer.
Yeah, yes, ma'am.
Tell me.
Yeah, so the answer that is given as a key is 1300.
Correct.
Um, so it has 400 primary turns and 1000 secondary turns.
Okay.
Um, Primary is connected to 520 volts 50 hertz supply.
Correct.
The value of voltage induced in the secondary winding
Yes, so you have basically N1, N2, the turns ratio you have, and the primary voltage V1. You are asked to calculate the voltage induced in the secondary, which is V2.
So it will be V1 by N1 equal V2 by N2, that way, right?
Correct,
So we have to find V2.
correct.
So
So
V1,
V2 by V1 will be N2 by N1.
yeah, V2 by V1 equals N2 by N1.
Correct. With that, you will get V2 as 1300.
5,
What is the
5.
problem there?
Oh yeah, I took it. Yeah, my mistake, ma'am. Yeah.
Correct, correct. Because I couldn't find out any mistake because today only I reviewed the this thing and what sir has pointed out for those 5 to 8 that was rectified. I couldn't find any mistake in the question you were talking about. That's why
Yeah,
I
I
was
got it, ma'am. And
yeah.
the 5 to 8 questions, those been updated on the portal, or is it
No,
yet?
no, no, no. As of now, it's not because today only it was reevaluated. Okay, so once it is done and the scores are pushed, then only you will be able to see that. So maybe by Thursday I can let you know the update on that. So as of now, you may not see it rectified because today only it was submitted. Okay, revaluation.
Okay.
So maybe after 2 or 3 days, once the scores is pushed, you will be able to see. If you have done it right, that will be getting reflected on your scores.
Okay, ma'am. Yeah.
And for 16 and 17 also, I mean, again, that question on transformer, the impedance matching in the transformer, many of you had done it right, but the question was actually like the turns for achieving this, the turns ratio is N1 is to N2 and asking for the value of N1 and N2. So it comes to that ratio is coming like 1 by 3. So it is something like you make it for N1 1 and N2 3 or 0.33 N1 something like that. Fine, which is the ratio is 1 by 3. But many of you have, I mean, I've done it right, but entering the values finally asking for the values for N1 and N2, some of you had made mistake for that question 16 and 17.
But we have entered 1 and 3 like in that order only.
Maybe I am talking about for others who had done it wrong.
Yeah, yeah.
Yeah,
Because mine was right. I remember it was 1 and 3 we have put and it was right.
yeah, fine.
Yeah.
And regarding one thing before,
Ma'am, graded assignment solution will be released in ma'am for week 11.
yeah, right from 9 you are supposed to get right. It's pending.
Okay, ma'am.
Am I right? Yeah, 9,
Yes,
10, 11 will be given to you tomorrow, and after the deadline of week 12, that will be given separately. So meanwhile, I was almost done with it, but meanwhile got occupied with some other work regarding the NSM, all those things. So I couldn't as such release it. So you will get the week 9, 10, 11 graded assignment solution tomorrow. And mock paper, you will get it by Saturday after the deadline of week 12.
Yeah. Can you release by hardly by Monday or Tuesday mock paper?
Yeah, mock paper you will mostly get it by Saturday, but I mean the mock paper is ready. We are waiting for the week 12 deadline to be getting over by this Friday.
Yeah.
But if it is not on Saturday, definitely you will get it by Monday because you have some the selection and all coming, right? So if some delay is there in the configuration work and all and getting it released, definitely you will get it by Monday.
Okay.
We will try
Sorry,
it on
you
Saturday.
referred to some selection. Sorry,
Which one, sir?
you mentioned that it might get delayed to Monday because of some selection.
No, no, election duty you have, right?
Oh, okay, okay.
So the concerned people may have some duty, and I don't know. So I am planning it on Saturday. So if not on Saturday, you will get it on Monday, so that you can see the coverage of the distribution between the weeks for the year. Similar thing you will have it for your NSEM also. How the portions are divided between various weeks, all those things. So you just basically, as always, we request you, even for the last time paper ESTC, you just thoroughly go through all the practice and graded assignments, all that has been discussed in the lecture, all the numerical problems in the lectures, as well as these quiz papers, mock papers, etc. That will give you the basic foundation, and then try solving extra also. That will be fine for you to do well for your NSEM. Okay. Screen is visible?
Yes, yes.
Yes. One second. So, as just discussed in the lecture, with reference to the low pass filter experiment that you were doing it in the last term while you were coming in person for the lab session. So, there you had actually plotted the magnitude response of the RC filter, low pass filter, right? So, actually, you have the this first order low pass filter circuit where you had one R and one C. So you have you can derive right now with what we have learned so far the transfer function of that low pass filter circuit. Then once you derive the expression for H of S, there you substitute for S equal to j omega, then you find the magnitude of that H of j omega, and accordingly you can get the magnitude response of the low pass filter. So that was the one. Since you had done it already, that was taken as a reference for your better understanding. So we can just go in a similar way, just to reinforce what we had learned through the lectures first, and then we can move on to the other examples of Bode plot. So what we basically, if you remember, try to recollect what you had done is, even in the, the corresponding weekly lectures also, low pass filter, if you try to remember, you will be varying from very low frequency, say some 10 hertz or 100 hertz, and then you will go increasing the frequency. You will go to 1 kilohertz, then 10 kilohertz. Like that, you will be increasing the frequency and go up till a very high frequency of the order of megahertz. Accordingly, you will be observing the magnitude of the output. So you can see in the case of the low pass filter, as you increase the frequency, the magnitude will be coming down, reducing, right? So it will pass low range of frequencies, and after depending upon the cutoff frequency, thereafter the magnitude drops. So since we are varying the frequency in a very large scale, that means starting from very low frequency and going up till a very high frequency, we may not be able to plot it in the ordinary graph paper. So we go for the talking about the log scale. That means the omega is increased 10 times. That means first we may be starting with 100 hertz, then we increasing it to 10 times. That means 1 kilohertz, then 10 kilohertz, 100 kilohertz, and so on. So we since the variation is large, we better practically we are able to plot it in a logarithmic, as already discussed even in the lecture, while you people would also had been done in the similar case. I mean, the logarithmic graph paper was available, but right now tools are available for getting these body plots. So we actually in the x-axis, if we plot the omega, that will be say 1, 10, 100, etc. You will have it of that order, the increasing order in the 10 times it will be. And y-axis we plot the modulus of h of j omega, that means the magnitude of the transfer function. And then you see what will be the typical plot for the corresponding circuit. So we take the example of the low pass filter right now. So being low pass filter, you know that the output is taken across the capacitor. V in is applied here to the series RC circuit. So this will be the reference. This will be your V in of S, and this will be across the capacitor will be your output. So V naught of S, what will be the expression? It is the simple voltage divider. So in terms of V naught of S, what will be V naught of S? V naught of S is across the capacitor.
Is V in of S into 1 by SC divided by 1 by SC plus
SC
R.
divided by
1 by SC plus R.
1 by SC plus R. So this ratio V naught of S by V in of S, we had talked in the last session that it is nothing but the Laplace transform of output to the Laplace transform of input, which is our transfer function. So we can alternately label it as or refer it as h of s, the transfer function of the system. So that will be 1 by 1 plus RCS. So here, if you substitute S equal to j omega, actually we have S, the complex number, which has got a real part and imaginary part, which is sigma plus j omega. The sigma is the real part and omega is the imaginary part. So here we typically go for the frequency response. So we vary the frequency and we are focusing only on that. So we here consider sigma equal to 0. So we are typically focusing on the y-axis in the S plane, and then there we vary the frequency, and accordingly we try to get the magnitude plot of this low pass filter. So S equal to j omega.
In this sigma plus j omega, which is the transient and steady part in that?
Which one?
Now S in the
No,
S plane.
actually, transient comes when you have those switching actions, right? So actually, as already even Anirudhan sir has mentioned in the lecture, that the experiment that you had done last time is actually finding out the steady state output, because there you are not typically doing something with these switches. You are not seeing anything like transient there. because you just set up the circuit and the things are settled, and finally what you were doing in the lab was the steady state output.
So this setting sigma 0, what signify actually? Setting sigma 0, what is the significance of this sigma 0? That's what I was thinking. It is transient portion, so that's the reason he's trying to set it 0.
So does it refer to this? I mean, steady state value or transient? We are talking about the frequency response. If you consider in the corresponding explain, this is sigma, this is j omega. So sigma equal to 0 is this point. There you vary the frequency and you are seeing. So that will be your that refers to your experiment what you had done. So that's why here we are uh, taking the sigma 0.
Okay.
Here we had not taken any, just like as the numericals, so many numerical problems that we have done in ESTC, we haven't taken any, initially it was in, the switch was in some position and then it was drawn, something like that. Then you may, you can analyze what was the voltage across the capacitor just after the switch is closed, all those refers to that I of 0 plus, all those refers to the transient values. But what the experiment that you had done is the steady state output.
Okay.
So substituting s equal to j omega, h of j omega, we will get it as 1 by 1 plus rc, here j omega. So just to write it as real part and imaginary part separate, so it will be 1 plus j omega rc, and to find out the magnitude I take the modulus. So modulus of h of
Uh,
j omega will be.
Ma'am, may I add one thing to that question? What I think Prabhanjan asked, or I think it was Hemant who asked about sigma.
Yeah, yeah.
Uh, so
Yeah, sir. Tell me, please.
I believe by setting sigma equal to 0, we are choosing a state for the circuit which will be critically damped. I mean, it will be in the resonant state. I'm not sure how will that be in case when we don't have L. Generally in RLC circuit, uh, I mean that's how it is described in the book. Uh, Means my understanding is not complete here, but I'm just sharing across what I means what I got to understand.
So just to add on to what you have referred right now,
Yeah.
I don't know for at least for those who are very beginners here. I mean, what the terms you are referring right now. I mean, underdamped, overdammed, all those things, and then those oscillation kind of things. All those we will be learning only in the control system paper, right?
Uh,
So as of now, many of them will not be aware of those things to understand, I think.
Ma'am, while doing Laplace transform, we came across some responses which had exponential terms in it, and then some which have
Correct.
sinusoidal terms to it, right?
Correct.
So what I meant by that is that by making sigma 0, we will be removing out all the exponential terms. We'll just be dealing with the sinusoidal terms.
Okay.
Okay.
This might means my understanding is not complete here, but uh, especially when we don't have L in this case,
Yes.
what does the resonant frequency mean? I am not sure, but by setting sigma 0, we are essentially reducing all the exponential terms to 0.
Okay.
Okay. We'll explore this further. No problem. Yeah. Thank you.
Yeah, yeah, welcome. I'm just learning as I'm going. This can actually be found in the appendix of the book that we were referring to in our previous term.
William Hague.
Yeah. The complex plane or frequency representation. That's
Okay.
where, yeah, you can refer to that book in case you want to.
Yes, we'll do it.
Yeah.
Okay, so we had just taken that example of that experiment that you had seen, which is the low pass filter, and we right now have written the expression for the transfer function of this low pass filter, so that we get it as h of s equal to 1 by 1 plus SCR, and by substituting s equal to j omega and then finding the modulus, we get the magnitude of the transfer function, which is 1 by square root of 1 plus omega RC the whole square. So now, if we try to plot it here,
1 minute. Just have a doubt. When you are taking the magnitude of h j omega,
okay,
the right side is the quotient, correct? On
right
the
side.
quotient, right side is the ratio of 1 by 1 plus omega RCJ, correct?
Yes,
So do you need to do the rationalization then take the modulus, or we can take the denominator directly?
you have the complex number only in the denominator, right?
Yeah, but then that modulus cannot be taken directly, no, as a denominator. We can do that as a mathematics.
For this thing, it is right only because you have numerator as 1.
Okay.
Suppose you had something like a plus jb by a minus jb and all, then you have
Then
to multiply it with the conjugate, all those things, and then get it. Here,
okay.
here for this particular case, the low pass filter we are talking about, where we have it like 1 by 1 plus j omega RC, numerator is 1. So
Okay.
for this is of the form a plus jb. So square root of a square plus b square will be the magnitude. So this will be fine.
Okay. Understand. Yeah. Yeah. Please go ahead.
So if we try to plot it accordingly, the magnitude response. So omega, this will be modulus of h of j omega. So as already discussed, we are starting from a very low frequency and then increasing 10 times and so on. So this will be in the log scale, omega, 100, 1000 and so on. I mean the powers of 10. So we have to analyze this as we had done it in the last term. So what we have is, if omega RC is very much less than 1, what will be this magnitude? It will be,
Ma'am, these 10, 100,000 are in log.
which one?
Ma'am, the x-axis, it is in log, 10, 100,000.
Yes, you are asking what are those 1, 10, 100?
Ma'am, like it is log 10, log 100, like that.
No, logarithmic paper, you will have that if you had seen that logarithmic graph paper, you can see that the values are plotted like the scale is non-linear. You will have 10, 10 to the power 2, 10, then 1000 and so on. So that only I have here. What here I have written like is just to mention that it's not the ordinary scale, that it is in the log scale that we have done it, since we are drawing it for the first time. Actually, if you could get one graph paper, yeah, I mean logarithmic paper, you can there see how it is being plotted. You will have some values being crowded to one portion, and then as the scale is increasing, there all that understanding how the scale is being chosen, you can get one logarithmic graph paper if you can and understand. So this why I have referred it like it's not the ordinary scales that we usually do. So say 1 unit is 1 unit in the x-axis, or say 0, 5, 10, 15, something like that, but it is increasing 10 times actually, higher orders of increase. So that is your logarithmic scale. So here, when omega RC is very much less than 1, what will happen to this magnitude? This denominator
Will be
can be
equal to 1,
approximated
ma'am.
as 1. So square root of 1. So 1 by square root of 1, it will be equal to 1. And what we do in frequency response generally, here we take that on the y-axis, we plot the magnitude of the transfer function in dB. dB refers to decibel. So modulus of, this magnitude in dB, we basically get it by taking 20 log to the base 10 this magnitude of h of j omega. So to get the magnitude in dB, which are the values plotted on the y-axis, we have to take that 20 logarithm of that magnitude. So here, while we are analyzing the circuit, when omega RC is very much less than 1, you can see that this denominator can be approximated to 1. So we get the magnitude to be 1. And now to get it in dB, it will be 20 log 1, which will be 0. So maybe till this omega equal to 10 it happens, then we can draw something like till 10 it is 0 dB, and after that what you have, if omega RC is very much greater than RC, what happens? The other case,
Ma'am, then the value is equal to 1 by omega RC, ma'am.
so magnitude
Magnitude.
will be,
But why you were saying till 10 it will be 0? Because RNC is not given here, no?
no. If say, I told you, if it is happening, suppose till 10, this is just we have taken, say for example,
Okay,
as
so
you say, we
suppose,
don't know the values. So once the values are known only, we can say whether it is still 1, it is 0 dB, or 10. Yeah, you are right. Say for example, if the 0 dB till is 10,
yeah, so
for
basically
example, I have taken.
at 10 it will become omega equal to 1 by RC, correct?
Correct.
Okay.
So omega RC is very much greater
Please
than 1.
repeat, ma'am. Please repeat the concept, ma'am, once again.
No. Sir was asking why this red line is shown till 10. It's just for an example. Why the 0 dB is up till 10? Because we don't know the values. We are taking the general case RC. We don't know the value of R and C. We are not doing it for some particular numerical example. So here, just I have drawn it for example. I have extended till the 0 dB line till omega equal to 10. Okay, the red line here. So now, yeah, what happens if omega RC, the other extreme case, when omega RC is very much greater than 1? You can see that this magnitude is equal to right now 1 by omega RC. So now that again in decibels, it will be 20 logarithm of this. So you will have
So minus 20 here, no? Because
why
omega,
minus 20, because you can see that 20 log A by B. So you can write it as log A minus log B.
yeah,
And
correct. So
so 20 log 1, that becomes 0, minus 20 log. So if you, for your understanding, I can write it like in dB, it is 20 log 1 by omega RC. So that will be 20 log 1 minus 20 log omega RC, because log A by B is log A minus log B. So accordingly, I have written like this. So this will be 0 minus 20 log omega RC. So you will have a line which is having a slope of minus 20 dB per decade. Decade means this increase of the with the power 10, then 20 dB. So this will have the, I have to show different actually.
This decade is actually log omega RC value, no?
Yes. So this will be the case. So as you had already pointed out, depending upon the value of R and C, we have to check whether up till what particular value of omega this rho dB line we have.
Minus will be there, no, ma'am?
Yeah, minus.
This omega RC much greater than 1 will depend on the RC. Then only you can. Yeah, it makes sense. Yeah.
Yeah. Okay. So this is for your low pass filter example where you had actually if you see the corresponding transfer function, you got it like this. So here you have one pole, right? Because if you equate the denominator to 0, you will have S equal to minus 1 by RC. So that minus 1 by RC is the pole of this transfer function. So this transfer function, which is the one corresponding to the slow pass filter, is a typical example of a transfer function where you have a pole. The next example shown in the lecture is where you have a single zero.
Yeah, can you mark the pole and explain that? 1 minute. The
Yeah,
pole is 1 by RC only, no?
minus 1 by RC. Yeah, it lies on the left half of S plane.
Okay.
So actually, depending upon, as you have mentioned, for particular value of R and C, this will this red curve shown here may shift to this side or this side.
Yeah.
I mean, for lower values of RC, you will get it like this, and may if the RC is higher, you may have still the curve shifting like this to the left of the one currently drawn. Okay.
Okay.
Ma'am, I have a couple of questions here.
Yes, sir.
So, on a general Bode plot, if I'm not changing the values of RC,
Okay.
how will the plot look like for a low pass filter?
What do you mean by you are not changing the value of R and C?
I mean, the red line that you plotted on this graph,
Okay.
the slope came into picture only when we are considering high values of omega RC,
Correct.
right? And does that mean that we are keeping R and C constant and it is just the value of omega which is varying?
Yeah, for that particular value of R and C, you will get one particular curve of this shape anyway. But where exactly that 0 to be etc. comes, that will be decided by those values. That's it. Right.
Okay. Okay. And when we carried out this experiment in our labs in last term,
Yeah.
there was a task given to us that we had to
Phase.
find the critical frequency, the cutoff frequency for that
Correct.
filter.
Correct.
Yeah. So looking at the at this plot, can we say something about that frequency? Means where will it occur or what? Where will it lie?
We actually say, I mean, in body plot, we refer wherever you have this change in slope, no? So those are the corner frequencies we generally refer that particular terminology we use. So here, this particular transfer function, we have it like 1 by 1 plus j omega RC, that is the denominator polynomial equal to 0, we get one this minus 1 by RC, that is the corner frequency as well as the critical frequency, I mean cutoff frequency here for this example.
So yeah, okay. You mean to say the corner frequency is nothing but the cutoff frequency?
No. Here corner frequency refers to here we can't explain because you have only a single pole, right? So when you take other examples, as you had seen in the other examples shown in the lectures, where you have zeros and poles, you can see that the slope is changing. At one place it is minus 20 dB, at some other place it is plus 20 or minus 40 dB, etc. So wherever you have that change in slope of this curve, right, those are the corner frequencies.
Yeah, but in case of this simple low pass filter, where I'll just
In
have
this
one
example,
pole.
yeah, it is.
Yeah, I'll just have one pole, and I need to determine the cutoff frequency for this low pass
Cutoff
filter.
frequency is this 1 by RC.
Yeah, how will means looking at this Bode plot, can I trace it on this plot?
Yeah, by means of the slope. From the slope, you will get the corner frequency. Here, that we just now referred that is the cutoff frequency, right? So we are just coming to that. I mean, from the body plot, how to from the slope of that. Say, for example, here this minus 20 dB per decade. How can you find out the corner frequency? Here, say for example, this 10 is the omega equal to 10 is right. 1 by RC is 10, correct?
Yeah.
That gives you the cutoff frequency.
If I can recall the objective of that experiment, point means 0.712, when the output voltage falls to that level, that's when we say that this is the cutoff frequency,
Correct.
right? So this transfer function is nothing but V naught by V1.
Correct.
So when V naught by V in becomes
You actually what you are referring to is, if I am right, you just tell me what you are talking about is what I am trying to tell you right now. You are telling you know that I mean at the cutoff frequency, the magnitude of the output will be 1 by root 2 times that of the input. That's the one you are talking about, correct?
yeah, yes ma'am,
Yeah.
yes.
So 20 logarithm of modulus of h of j omega is right now we are talking about. So 20 logarithm of v naught by v in. So you can say that it is 1 by root 2, correct? So it
Yeah.
corresponds to minus 3 dB frequency.
Okay.
Cutoff frequency is, that's why called as the minus 3 dB frequency.
Okay, so this is a constant value, is it? Minus 3 dB.
Minus 3 dB frequency we refer it to because in dB it is minus 3 and dB scale, and otherwise we know that at the cutoff frequency the output amplitude is 1 by root 2 times the input, and that you take it to the dB scale, you will get it as minus 3 dB. That's why the cutoff frequency is referred as the minus 3 dB frequency.
So how will this look on the Bode plot?
In the border plot you have to see that where that 0 dB line comes, correct? Then from that you subtract 3 dB to come to minus 3 dB, and then project it to the frequency, I mean x-axis. This is 0 dB line, right?
Yeah, yeah.
So minus dB refers you subtract 3 dB from there. That means somewhere here, correct?
Okay.
Okay.
Okay, okay, okay. Okay. So the projection that we are seeing on the x-axis now is the cutoff frequency.
Yeah, you take this from the 0 dB line, you subtract 3 dB, so that refers to that minus 3 dB, and that project onto the this one will give you the cutoff frequency.
Okay, 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 okay. Yeah, it's clear now.
Yeah.
Thank you.
Yeah, right. So yeah, we were talking about this particular example of the low pass filter had one pole, and the next particular example chosen in the lecture is just to start with simple examples, is the typical case where we have a single zero, so that we can right now see once again. Yeah, it was h of s is
Just on a lighter side,
okay.
our circuit should aim to behave between zero and pole, or I mean, how it's supposed to behave in real design? I am asking.
No, no. Can you just repeat your question?
Now, suppose we are designing a circuit and you want to check the behavior for different frequencies. So we should aim for behavior of circuit more stable between zero and pole, or it should be towards zero more or towards pole more. So what condition could be more appropriate?
Behavior of the circuit means what do you mean? That particular system will have anyway. It the I mean, how many zeros and poles are those will be defined, right? Once if you have that mathematical model of the system, I mean the transfer function. If you know,
No, like see, there are texts called an electrically stable circuit. So which circuit could be considered as stable? It is like
yeah. First,
between.
you're talking about stability. Stability and all. Right now, we can't talk about that. For we consider that root stability criterion. If you know. Correct, all those things will be discussed in the control system paper. We will be finding out the root array and then we check for certain things. Accordingly we talk about the stability, is it marginally stable, all those things. So if you are referring to understanding the stability of the system,
Yeah.
we have to learn more things like Ruth Hurwitz criterion, root stability criteria, all those things. So those are pure control system paper concepts. So you will learn it in that control system paper.
This is
Even
optional or compulsory? This is optional paper, no?
yeah, I think it's one of the elective. I have to just check it. Control system
Okay.
paper have this more insight. Even if you have gone through all the lectures of this week 12, even Bobby sir would be mentioning about that approximations that you would learn in the right, because this as now what you're talking with this linear line and all, it is an approximation. Actually it should come like a smooth curve. So you have what is called as first order approximation, second order approximation, all those things. So those are typical things that you will be learning in that purely that control system paper.
Yeah, sure. Understand.
Here also what we you had learned this Laplace, this S domain and all, the key concepts we had covered. Even the other things that you haven't learned, called region of convergence, etc. In the case of this Laplace, those are the things that you will be learning in the upcoming term. I mean the signals and system paper.
Okay, okay.
So as of now, just to get into the idea of this frequency, one of the frequency response plots, which is your Bode plot, you have other plots like polar plot and all. So
Yeah.
those you may be exploring in the control system paper.
Okay, understand.
So H of S, uh, one with the one single zero. You have even I think in your engineering mathematics also you would have learned these poles and zeros, finding poles and zeros. Then what you have like pole zero cancellation, all those
Yes,
things.
yes.
So
Yeah,
yeah,
yeah.
so this is a I mean vast area where you have to analyze, understand so many things. So only the key things have been discussed so far through this course.
Okay, understand. Thank you.
So 20 into what was the example? Let me just check. Yeah, 20 into 1 plus s by 100. So h of j omega will be and the magnitude will be taking the modulus. So that will be 20 into square root of 1 plus omega by 100 the whole square. So taking it in dB, what you have, you will have 20 log 20 plus 20 log, correct? Am I right?
1 by 2 will come, na? 10 will come, na?
Yeah, 20 log root AB. So that will be the then only you, when you get rid of this radical, you will have that 1 by 2. Am I right?
All are with respect to base 10, na, ma'am?
Yes, our base 10. So you will get this term when you compute, 20 log 20, that will come to 26 dB. Log is to the base 10. So if you check it in your calculator, you can see that evaluating as 26 dB. This 20 log 20. So if you one second. So this will be 26 dB. Then what you have is, you will have a positive slope. So that will be plus 20 dB per decade. If you have this omega increasing 10 times, so you will have that. Say for example, here it is actually happening at 100. Omega equal to 100. So with that, we try to understand that a pole will have the impact of, like, this slope is minus 20, will introduce a slope of minus 20 dB per decade in the body plot, magnitude plot of the body plot, and a zero will be just the reverse. It will be increasing the slope. So it will have the impact of plus 20 dB per decade on the slope of the magnitude plot of the body plot. Okay, so this will be the key idea for doing other numericals where we have both the cases of, both zeros and poles in the transfer function. So zero, let me just take the sample. Yeah, this particular example.
Could you please once again explain in the case of pole how it is minus 20 dB per decay coming, ma'am?
Here we have shown, correct? This is fine. 20 log 1 by omega RC. So that is written as 20 log 1 minus 20 log omega RC. So the first term log 1 being 0, you will get it as 0, and then minus 20 log omega RC. Now omega here you can see we are increasing it of the order of 10, right? 10 to the power. So omega, if it is 10 times, you can see that that will be becoming minus 20 dB. Correct?
Means omega, if we put the value of omega equal 10, na, that will be minus 20 dB.
Yes. Okay. So 0 minus that 20 log this one, that becomes minus 20 dB. So accordingly, you will have one pole always introduces a slope of minus 20 dB per decade to the magnitude plot of the body plot. Similarly, by means of the second example where you had the transfer function containing a single 0, because here you don't have the denominator polynomial. Numerator polynomial equal to 0, you will have only that is equal to minus Z1. Okay, so that happened here at this frequency, which is 100. So if you take the magnitude of this, you can see that it is 20 log 20 plus 20 log the square root of 1 plus omega by 100 the whole square. So this 20 log 20 will be 26 dB, and then this will give you a plus slope of positive slope, which is plus 20 dB per decade. So this will be the key idea that you should keep in mind for the drawing Bode plots for any given transfer function. So we can take now another example where you have both 0 and pole. We had just now seen first through the example of low pass filter, only one pole you had. In the second example, only a single 0. Now a general example where you have both. So accordingly, how to there manipulate things, we can see just now. So what was the example? Yeah, h of s is 2000 into s plus 0.5 by s into s plus 10 by s plus 50. So just before what we had discussed, how to find out what are called as the corner frequencies. Corner frequencies are the frequencies corresponding to where you have a change in slope in the body plot. So generally, if we can represent something like this, just I am taking the same representation as discussed in the lecture. For that magnitude part or constant part, A into 1 plus S by Z1 divided by S into 1 plus S by P2 into 1 plus S by P3. This is the generalized form that has been written corresponding to this particular example, which has 1 0 and 3 poles. So you have pole 1 0 from this term, then from the 3 terms in the denominator you will have the 3 poles. So if you observe the expression, that one of the poles is at origin because s equal to 0, or you can alternately write it as s plus p1 where that p1 is 0. So one pole is at origin, then other two are, you can write it like of this form. Okay, and then so we can better first write this given transfer function in this form so that we can find out the corner frequencies. So 2000 into
Oh, ma'am, I am having one doubt in low pass filter.
yes.
Ma'am, in last time when we were plotting low pass filter, like there was voltage which was above x-axis and then it was getting down. But here we are taking it on 0 in x-axis and then we are getting in minus.
No, I don't understand which example you're talking about. The one with zero or one with pole?
When low pass filter, like in last time, there used to be at output some voltage above x-axis, like what is input, that is output, and
Correct.
then it was getting low as the
Yeah,
frequency
yeah,
was
you are
being.
talking something like this, right? You are okay. Your doubt is you had it, you obtained it like this, but
Yes,
right now
yes,
I
ma'am.
have drawn it like this.
Yes, ma'am.
But you had drawn it in the ordinary graph last time, right? It was not in dB. Correct.
I'm like, if low pass filter is allowing low frequencies, then why it is coming 0?
Yeah, I will just make you understand here. The thing, both are the same. That means you get the same shape. What is the difference here is you would not have seen where you introduced with the dB scale last time. No, you are just finding out the response like this. Correct. Last
Yes,
time.
ma'am.
Yeah.
Yes.
So for depending upon the cutoff frequency of your given low pass filter, you would have got something like this, and you will have like this. I mean, for certain range, here we have omega, and here we have that magnitude on this y-axis. So if you see the output amplitude for certain range of frequencies, you will have the output amplitude same as that of the input. That means this portion. After that it drops. So where it drops, that cutoff frequency, you would have taken where that output is 1 by root 2 times amplitude, output amplitude is 1 by root 2 times the input. That projected on x-axis, you would have find like the cutoff frequency. This is what sometime before sir was asking how to relate it like. So here 20 log for this portion, right, where your output amplitude is same as that of the input, 20 log V naught by V in. So V naught is equal to V in, so 20 log 1. Because V naught equal to V in, that ratio becomes 1. So that will be corresponding to 0 dB. That is your this line. Thereafter what you have, everything will come in minus dB. That is this portion.
So, ma'am, like if I am getting 0 dB, that means I am getting no signal at output.
0 dB refers to the range of frequencies for which your output amplitude is same as that of the input. That means the frequencies that the low pass filter pass.
Okay, 0 means there is no change.
0 dB refers to that. That's right now exactly here what I have written. You are confusing with the ordinary plot with the this dB plot. Please understand what you had done last time is same as that we described here, but difference in that scale we are talking. Okay, so here do you remember this curve that you are getting? This is the frequency response of the low pass filter, where you have this portion for it will pass a certain range of frequencies, after which the output amplitude is reducing. And to
Yes.
find out the cutoff frequency, you will be finding out the point where your output amplitude is 1 by root 2 times that of the input. So that is shown here, and that projected on x-axis will give you the cutoff frequency. That is 1 by RC. Omega is 1 by RC. That is the cutoff frequency. Now, this flat portion where you have the output amplitude same as that of the input, that you substitute here. How just now we had discussed that magnitude in right here you had done it only in magnitude of h of j omega on y-axis. You were not taking it in the dB scale. Now take it to the dB scale. What you should do, you have to take 20 logarithm of modulus of h of j omega to get the modulus, I mean magnitude in dB. So 20 log V naught by V in. This portion, flat portion, refers where your output amplitude is same as that of input. So V in, V naught equal to V in. So this ratio V naught by V in becomes 1. So 20 log 1, that becomes 0 dB. That is this portion. Then thereafter you see you will get the cutoff frequency where this output amplitude is 1 by root 2 times. That I just now, just before when sir has pointed out, I had shown it you like 21 by root 2, that will become minus 3 dB. So minus 3 dB, and then again the other portions you will have it like this. So thereafter all the things come in minus dB, because this is the reference rho dB. So the shape of the curve will be the same, but the scale is different. So 0 dB doesn't refer to no change. 0 dB, means the range of frequencies that it pass. Means the output amplitude is equal to the input amplitude. Output is equal to input.
Okay, okay. I got it.
Yeah, so when you try to write it in the standard form like A into 1 plus S by Z1 by S into 1 plus S by P2 into 1 plus S by P3, so that will be 2000 into 0.5 into 1 plus S by 0.5 divided by so that will be 20 by 4 into 0.5, so 2. Okay, so this will be your h of j omega. So now you have 1, 0, 3 poles. Okay, so Z1, these zeros and poles are the corner frequencies actually. Okay, so 0, Z1 you will have. So accordingly, where it happens, 0.5. So till 0.5, it will be 0 dB. And after that, 1, 0 introduces a slope of plus 20 dB per decade. So that will be going like this. This will be corresponding to this 0, Z1, which is corresponding to this term. Then P1 corresponds to this pole at origin. Okay, so a pole will introduce a slope of minus 20 dB per decade. So you will have actually continuous decline of this. So this the slope will be minus 20 dB per decade, and at 1 it will be 0 dB. Correct, 20 log 1 is 0 dB. So at 1 it will be 0 dB. So this will be the thing, and then corresponding to P2. P2 is this term, the second pole. So that corresponds to omega, I mean it is 10, correct? So here it was 0.5, so better I will draw it after that. So till 10, it will be 0 dB. And after that, again, pole introduces a slope of minus 20 dB per decade. So this will be and finally the last term, the third pole, this term. So that corresponds to 50. Then that minus 20 dB per decade. Then what you have? 2, this term, constant term 2 in the numerator. So that will be
Please explain all the terms, ma'am. Z1, P1, P2.
yeah. Here this one, to find out the corner frequencies, we generally make it of the form this a constant term if you have in the transfer function. So a into 1 plus s by z1, where z1 refers to that 0 of the transfer function, divided by s into this s term refers to a pole at origin. Okay, because you can write it alternately like what, s plus p1, okay, or 1 plus s by this one, so that is a pole at origin. Then 1 plus s by p2, 1 plus s by p3. So accordingly I have in this standard form I have alternately written this transfer function like this, and simplifying I will get this expression: 2 into 1 plus s by 0.5 by s into 1 plus s by 10 into 1 plus s by 50. So first you have this term, the numerator. So 1 plus s by 0.5 gives you a 0. So that is referred as here z1 equal to, so what is the value here? 0.5. So till 0.5 you will have 0 dB, and after that the slope is increasing at plus 20 dB per decade. Okay, then P1 is the pole at origin. So P1, you know that a pole introduces a slope of minus 20 dB per decade, minus 20 dB per decade, and so that will be that will have the 0 dB line at 1, because 20 log 1 is 0. So this will be the line in general for that P1. Then P2, what we have is, it corresponds to this term 1 plus s by 10. So till 10 it will be 0 dB. After that it is minus 20 dB per decade. Similarly, the last term corresponds to P3, 1 plus s by 50. So till 50 it will be 0 dB. After that it will be declining at a slope of minus 20 dB per decade. So these are the things, considering them individually. Now actual plot will be adding all these things, and towards the end we had considered this constant term also, this a equal to 2, this one. So that will be 20 log 2, which will give you 6 dB. So altogether you have to sum these up to get the original, I mean the body plot of the given transfer function. So how to add it up, we can see right now.
Ma'am, for P1, ma'am, two graphs are there, ma'am. Looking 0 dB up to 1.
P1 actually, it is, I mean, how to explain to you? It is a continuous line which is having a slope of minus 20 dB per decade. Like here, how if you refer, see the case of P2 and P3. P2 you had till 10 that 0 dB, and then from that it is a decline. P3 till 50 it is 0 dB line, and then it is a decline. Similarly, if you take P1, you can understand that 0 dB corresponds to this 1 at 1, because 20 log 1 is 0, right? So that is shown here. So right now, if we try to plot the magnitude plot, so let us write the values according to the given transfer function. So what we have is 0.5. Okay, so you can see that this 0 corresponds to 0.5, and the P1 pole corresponds to 0, P2 corresponds to 10, and P3 corresponds to 50. So if you try to plot it there, first this one 0, because that is the at origin, right? So till starting from origin, you will have that decline of minus 20 dB per decade, and what you have is at 0.5 here. If we take at 0.5, you will have the impact of the 0 as well. Okay, so 0 is introducing a positive slope, so plus 20 dB per decade, and this line is extending throughout. So what happens at 0.5? This plus 20 dB per decade and this minus 20 dB per decade gets cancelled, and that becomes 0.
Ma'am, please repeat. Ma'am.
I mean, first you closely observe the values. What are the values here? I mean, this one, corner frequencies, 0.5, then this 0, 10, and 50. Correct? So 0.5 is corresponding to this 0. This 0 is, I mean, origin, that is, you have this pole P1, then 10 corresponding to this pole P2, 50 corresponding to this pole P3. So if you try to add all these and find the magnitude plot of the given transfer function, then what you have is, first this you start with the 0. You how do you go in that order? 0, 0.5, 10, 50. That is the order, right? 0, 0.5, 10, 50. So 0, what you have, it corresponds to pole. So pole introduces a slope of minus 20 dB per decade. Okay, then at 0.5, because of this 0, because of the influence of this Z1, you have a slope of plus 20 dB per decade. So what happens when you come to 0.5? When you come to 0.5, you have the impact of this P1 as well as Z1, where P1 introduces a slope of minus 20 dB per decade, and Z1 introduces slope of plus 20 dB per decade. So both gets cancelled each other. So that there it becomes 0 dB. Correct. So until then, it will be the impact of this P1, which is a decline of at the rate of minus 20 dB per decade. So till From 0 to 0.5, because of the impact of this P1, this will be minus 20 dB per. And 0.5, from 0.5 to what you have up till 10, correct? It will be extending like 0. This is 0 dB. Then at 10, what you have, because of the influence of this pole P2, you have a decline of minus 20 dB per decade. So I will draw it like this. This line should be parallel to this because both are having a slope of minus 20 dB per decade. Then at 50, what you have, because of the influence of P3, minus 20 dB per decade. So already you have minus 20 because of the influence of P2. Then one more minus 20 dB, so that makes it minus 40. So it will be rapidly. I mean, here you have a. Let me mark it like 10 to 50, right? So better I will redraw so that I can show it explicitly. So starting from origin till 0.5, then up till 0.5 it was 0. I mean, no, it was minus 20 dB per decade because of the influence. So I can, better for understanding, this is the influence of P1. Okay, then P2, so till 10 it is 0 dB. This line maybe I can shift downward so that ~50. So that will be minus 20 dB per decade. And after at 50, what you have, one more minus 20 dB per decade because of the influence of P3. So with this minus 20 and this minus 20, it becomes minus After this 50, it becomes minus 40 dB per decade. Okay, so this will be the plot when you add it up. And one more thing that we need to correct in this plot is when it actually crosses the 0 dB. This is a 0 dB line, right? So that we have to see. This was 12 dB. Ten to 50, 6. Okay, anyway, the approximation is something before 50, it has to cross the this 0 dB line. So you may have to shift this 50 this side. Okay, so we see these free, values in the from the transfer function 0.5, then 0, 10, and 50. So that is drawn here 0, 0.5, 10, and 50. Then what we have is the Z1 up till 0.5, it is 0 dB. Then being the 0, it introduces a positive slope. P1, it is the pole at origin. So it introduces a minus 20 dB per decade, and that crosses the 0 dB line at 1. Then P2 is corresponding to this term. So up till 10, it is 0 dB line, after which it is a negative slope minus 20 dB per decade. P3 corresponds to this term 1 plus d omega by 50. So up till 50 it is 0 dB line, and thereafter minus 20 dB per decade. So right now and finally this constant term 20, a equal to 2, not 20, 2, a equal to 2. So 20 log 2, that will give you 6 dB. So now you club all these together to find out the magnitude plot of the given transfer function. So from 0 to 0.5, what you have is, here it is saying what? Because of the influence of P1 from 0 to 0.5, it will be a negative slope of minus
Minus
20 dB
20.
per decade. Okay, so that is drawn here up till 0.5. Because of the influence of P1, it is minus 20 dB per decade. And from 0.5 to 10, what you have is from 0.5, because the influence of Z1 is plus 20 dB per decade, and influence of P1 is minus 20 dB per decade, so that both gets cancelled and we get it as 0 dB, and that 0 dB, because of the influence of P2, it continues until 10. So in effect, from 0.5 to 10, the 0 dB line extends. So this is the 0 dB.
Ma'am,
Then
0 dB will not coincide with the x-axis, ma'am.
no, actually, I mean this one. I
0
mean,
dB,
what
0
to
dB.
say?
Because you are saying 0 dB,
So yeah,
it will coincide with x-axis line, ma'am.
no, what is the value here? You have it at some 6 dB or 12 dB, right? This one, because of this A equal to 2. Am I right?
Yes, ma'am.
That, I mean, that increase or decrease will not happen. It will be staying constant until from 0.5 until 10 till 10. Then at 10, what you have, the influence of P2 is minus 20 dB per decade, and P3 it is continue like this. So in effect, you will have from 10 till 50, it will be a negative slope of minus 20 dB per decade, and at 50, you will have the influence of P3 also, which introduces another minus 20 dB per decade. So that becomes after 50, it will be minus 20 plus minus 20 minus 40 dB per decade. So that will be the adding it up all together. Fine. So I think this three examples will give some idea. One pole, one zero, and you have the case of both zeros and poles. I think more on the Bode plot we can continue on Thursday, so that I can take some 10 or 15 minutes for the other questions from the practice, so that with the Bode plot questions on Thursday we can wind up with week 12. So I will just take the example from the practice on those other simple questions. So if I can share you the screen. So the first question from practice is given a transfer function, finding out the corner frequencies. Okay, so better that we can once again see how from the slope of the Bode plot to find out the corner frequency. So that also I keep it aside as of now, so that you will get a better idea in the next class doing more discussion on Bode plot. So I will just finish with the other questions. The second question is, consider x of t is the input and y of t is the output of a system. The system is described by the differential equation and it is given, and you are asked to find out the transfer function. Seven plus 12, 1 plus 2. Okay. Question 2. The differential equation is, let me just see.
Screen not visible, ma'am.
What I write is not visible for you?
No, ma'am.
Right now?
Yes, ma'am.
Okay, so what was the question? 7. Sorry, d square y by dt square plus 7 dy by dt plus 12 y of t. Equal to dx by dt plus 2x of t. This is the differential equation describing the system. You are asked to find out the expression for the transfer function y of s by x of s. So tell me the expression in the s domain. So 1 d by dt will be the effect of multiplying by
Ma'am, is d square plus 7d plus 12 in this way, ma'am?
yes. What is the doubt?
Yes. That's what I'm telling.
Second question, practice.
Yes.
So tell me the expression in the S domain. 1 d by dt is in effect multiplying by s, right? And d square by dt square, I mean second order derivative refers to multiplying by s square. So accordingly, what will be the expression in s domain? D square by
S
y of d
square,
square
S
becomes
square ys, ma'am,
s square y of s
plus 7
plus 7 yes
S.
y of s
S y of s.
plus 12 y of s equal to yes x of s plus 2 x of s. So y of s into s square plus 7s plus 12 equal to x of s into s plus 2. So y of s by x of s will be s plus 2 by s square plus 7s plus 12. So that is s plus 2 by s plus 3 into s plus 4. Third question, the transfer function of a system is given by h of s is 10 divided by s square into 1 plus 3s into 1 plus 4s. Which of the statements is false? The transfer function has 3 poles. Transfer function has 1 pole at origin. This actually better to fine tune the statements, I think, because you have multiple poles at origin, right? I mean 2 poles at origin because it is coming s square. So the transfer function as only 1 pole at origin or something like that. Being a practice assignment, this is fine, but the sentence should be somewhat clear. The given statement should be clear, I think, more clear. The transfer function has 3 poles. How many poles it has got? If the transfer function is, I think you will have the practice assignment with you because I'm not sharing the screen right now. I mean the practice assignment question I'm not sharing. Maybe I can write it here. The transfer function is h of s equal to 10 by s square into 1 plus 3s into 1 plus 4s. Question 3. What is that? S square into 1 plus 3s into 1 plus 4s. So the given statements are transfer function has no zeros. Transfer function has 1 positive pole and 1 negative pole. So all the poles are negative. So that is the thing, fine. But the other statement should be like second statement, the transfer function has 1 pole at origin. Only 1 pole means that also becomes false because it has got 2 poles at origin. So like that, maybe I can update it tomorrow, these statements. So that is fine, okay. Then question 4. The transfer function of a system is
Ma'am, ma'am, 2 poles at origin, ma'am.
So here the given transfer function, which is h of s equal to 10 by s square into 1 plus 3s into 1 plus 4s. So you will have 2 poles at origin because s square it is, correct? This term s square in the denominator equated to 0, you will have 2 poles at origin. Am I right? Because
We
the
have seen
order
this.
of it is s square. Earlier it was simply yes in the example that we had taken here. it was simply S. So you had only one pole at origin. Here it is S square. So you have two poles at origin, multiple poles at origin. Okay, so that is one thing. And the other two poles are S equal to minus 1 by 3 and S equal to minus 1 by 4. Correct? Those two are negative poles. So you don't have positive. Correct?
Yes, ma'am.
That is the thing. So the one thing I was talking about was I will make the choices, the statements given as choices will more clear because the choices are transfer function has three poles. Actually, it has to be four because you have multiple poles at origin. Okay, so those updations I will do.
Ma'am, is third option is correct, ma'am? Please see. The transfer function has no zeros.
Yes.
So that is a
This
false
I will
statement.
fine tune the statements. Okay. So just understand what are the poles and zeros. That's it. I will fine tune the statements. I will update it. I do remember the updations in the other weeks as well. I will do it. Okay. I will just let you know in 1 or 2 days. I couldn't find time to complete it. The transfer function of a system is given by h of s. Next question. I'm going to the fourth question. The transfer function of a system is given by h of s equal to s minus 2 divided by s plus 1 by s plus 1 into s plus 3. The response for a unit step input is given by. So I will write it for you. H of s equal to I write s minus 2 by s minus 2 by s plus 1 into s plus 3. S plus 1 into s plus 3 is the transfer function given, and you are asked to calculate the response of the system for a unit step input. So response of the system means y of s is being asked, and step input is the unit step is the input. So what will be x of s?
1, ma'am.
Is it 1? Unit step, not impulse.
Yes.
So what will be x of s?
1 by s.
1 by s. So y of s by x of s is given to be s minus 2 by s plus 1 into s plus 3. So y of s will be h of s into x of s. So that will be s minus 2 by s plus 1 into s plus 3 into x of s will be 1 by s. So that will be, so if I can write it by partial fractions, a by s plus b by s plus 1 plus c by s plus 3. Find out these values. So a into what, s plus 1 into s plus 3 plus b into s into s plus 3 plus c into s into s plus 1, that will be equal to this s minus 2. So equating the coefficient of s, what do you get? Here it will be s square plus 3s plus s, so 4a. Here it will be 3b. Here it will be c equal to 1, equating the coefficient of s. Then equating the coefficient of s square, what do you get? Here it is a, here it is b, here it is c. So a plus b plus c equal to 0. And equating the constant terms. It will be 3a plus 3b plus c equal to minus 2.
The answer found out, ma'am.
Answer?
I have found out the answer, ma'am.
Yeah, tell me.
A equal to minus half, B equal to 3 by 2, and C equal to minus 5 by 6.
A equal to minus 2 by 3, B equal to 3 by 2, and C equal to minus 5 by 6.
No, I have got different answers. A equal to minus half, B equal to 3 by 2, and C equal to minus 5 by 6.
Just check it.
A equal to minus half, I have got, ma'am.
Yeah, just recheck that.
Okay, ma'am.
Have you checked?
Yes, ma'am. A equal to minus 2 by 3, ma'am.
So A is minus 2 by 3, B is 3 by 2, and C is minus 5 by 6. So substituting that here, you will get y of s as minus 2 by 3 by s plus 3 by 2 by s plus 1 plus minus 5 by 6 by s plus 3. So when you take the inverse Laplace transform to get y of t, which is the response of the system to the unit step input, it will be what was a? A was minus 2 by 3. So minus 2 by 3. So inverse of 1 by s. So minus 2 by 3 plus 3 by 2 into e raised to minus t plus minus 5 by 6 into e raised to minus 3t. So that I think it's fine because we had already done all these things in the week 4 and week 5. So I think only one more question on the transfer function, which is the last question, and the remaining are on Bode plot. So better I stop it here. So on Thursday we will just continue more examples on Bode plot. We will make it thorough how to given a transfer function, how to draw the Bode plot, or the other way out from the Bode plot, how to figure out the transfer function of the system. Then some basic understanding regarding this poles and zeros. So after which we can try solving these questions on this Bode plot from the practice assignment. Okay, so by Thursday we will be winding up with the week 12, and by Monday we can start the revision session week wise. Okay, so before you come on Thursday session, request you to go through once again the discussion on the Bode plot, the lectures discussion plus the numericals solved. First, you try it from your side, the practice assignment questions, so that a second discussion during the live session will make you effective. Okay. Fine.
Yes,
Shall we stop it here?
yes, ma'am. Thank you, ma'am.
Yeah. Thank you, everyone.
Thank you, ma'am.
Yeah. Thank you.
Thank you.
Thank you.